Sharvari? What we have explained till here? Okay, clear. Good. चलो, going up ahead. सेमीकंडक्टर्स में हम लोग लिखते हैं कि अगर आपका एनर्जी बैंड गैप 3 इलेक्ट्रॉन वोल्ट से कम है तो ये वैल्यूज इंपॉर्टेंट है. ये सब ऑब्जेक्टिव में पूछा जाता है. अबाउट 3 इलेक्ट्रॉन वोल्ट सेम आपके इंसुलेटर्स है 3 इलेक्ट्रॉन वोल्ट से कम है. फॉर एग्जांपल सिलिकॉन में आपका रहता है 1.72 इलेक्ट्रॉन वोल्ट और जर्मेनियम में आपका कुछ 0.6 इलेक्ट्रॉन वोल्ट है. तो it is less than 3 electron volt. So such type of materials are called as semiconductors. But overlap नहीं होता. और ये जो बैंड गैप है कंपेयर टू कंडक्टर्स ये ज्यादा है. तो at room temperature you will not find too many free electrons. So therefore we say that the number of electrons in the conduction band are very less. And that is why the name semiconductor. They don't conduct very well unless you add certain impurities. You can artificially improve the conductivity, and that's how they are used. We add some impurity and then we use them like semiconductors where they actually can conduct very nicely. All right, can we go ahead from here? So now we are going to talk about an intrinsic semiconductor. So when we talk about intrinsic semiconductor, that means a semiconductor where no impurities are added. We are going to add certain impurities later on. But initially we'll talk about the semiconductors like silicon and germanium where you have not added any impurity. And without impurity, we will try to analyze how they function. So silicon and germanium are semiconductors, we know that, and we also know that they have 4 valence electrons. So how do they form bonds? So you see that each silicon atom will form covalent bonds with 4 neighboring silicon atoms. Okay, so totally 8 electrons will be obtained in this formation of a covalent bond, where we say that the 2 electrons are actually shuttling back and forth between the 2 atoms. Okay, so आपका जो bonding होगा सिलिकॉन और जर्मेनियम में आप क्रिस्टलाइन स्ट्रक्चर में देखेंगे तो ये कोवेलेंट बॉन्ड है. और इस कोवेलेंट बॉन्ड में बॉन्ड आइडियल बॉन्ड हम अभी देखेंगे नेक्स्ट स्लाइड में कंप्लीटली फिल्ड अप, कंप्लीटली फिल्ड. एवरीथिंग इज वी आर गोइंग टू स्टार्ट. आइडियल का मतलब है 0 केल्विन. 0 केल्विन में पहले एनालाइज करेंगे where the bonds are not broken at all and all the covalent bonds are intact because no energy has been given because of temperature. So all the bonds are completely filled. All right, so can we go ahead and see that diagram of the covalent bond? So that will look like this. So here you have your silicon or germanium atom which is forming covalent bonds with, let's say, talk about this one, it's forming with 4 other silicon atoms, and each bond has the 2 electrons which is shuttling between the 2 atoms out here, and all of them are filled up. And as I told you some time back, this is an idealized representation. Okay, it is an idealized representation. That's why we are saying we are overemphasizing the covalent bond. It shows an idealized picture where none of the bonds are broken, because if you provide some thermal energy, then what happens to the valence band electrons? They can go to the conduction band. So from the perspective of energy level, when you talk about electrons going from valence band to conduction band, in the from the perspective of the bond structure, it is actually breaking of the bonds. So there are 2 ways of visualizing the same phenomena. So maybe in your chemistry you might have seen that, okay, bond break ho gaya, like that you might have studied it. But from the energy band diagram, it is actually the valence band getting sufficient, the valence band electrons getting sufficient energy to go to the conduction band. Only then it is possible to break away. So as the temperature increases, and some thermal energy becomes available, some of the electrons are going to break away and become free electrons. That's what we are going to expect in an intrinsic semiconductor. Intrinsic semiconductor का मतलब है no impurity added. Again, I'm repeating. All right. So is this picture clear before we go ahead? Mohit? Okay, picture is clear. So now we will see that what happens when the temperature increases. Temperature increases does not mean that I am going to heat up the semiconductor with some fire. That's not what I'm saying. We are talking about room temperature. Okay, 27 degrees centigrade, room temperature. You get sufficient thermal energy if that room temperature corresponds to an energy in terms of electron volt, which is sufficient for the electrons to go to conduction band, then the bond will break. And as you can see here, we have shown that bond which is broken here. ऐसे नहीं कि सभी बॉन्ड्स टूट जाएंगे, कुछ यहाँ पे टूटे हुए हैं, एक हमने यहाँ पे तोड़ दिया है, और ये एक थर्मली जनरेटेड, हम इसको बोलते हैं थर्मली जनरेटेड फ्री इलेक्ट्रॉन हम कहते हैं। और जब ये फ्री इलेक्ट्रॉन क्रिएट होगा, तब ये जो बॉन्ड है यहां पे एक वेकेंसी है, देयर इज अ वेकेंसी देयर आउट देयर, एंड दीज वेकेंसीज इन सेमीकंडक्टर्स वी कॉल देम एज होल्स। और सेमीकंडक्टर्स और कंडक्टर्स में एक इंपॉर्टेंट डिफरेंस ये है कि इन कंडक्टर्स द ओनली method or charges which can contribute to the current is basically electrons. You cannot have holes there. But in the case of semiconductors, we have two types of charge carriers. One is these thermally generated free electrons, and we will be studying now that how these holes can also contribute to charge flow. Absence of an electron, which is a hole, can also contribute to flow of charges. So in some theory questions they may ask objective that the type of charge carriers in semiconductors are electrons and holes both, but metals में जो होते हैं वो सिर्फ electrons रहते हैं. Correct? Okay, so now we are going to see that how this hole is going to behave like an apparent free particle with a positive charge. Okay, so there is a saying that there is a proverb in English which says that the grass is always green on the other side. You have heard of this? Grass is ever green on other side. Now, what does this statement have to do with semiconductor physics? In fact, this particular statement I found in one of the standard books which we refer for electronics and engineering, that's Millman and Halkias, uses this phrase to explain that why this hole can actually contribute to flow of charges. So let's see that in our next slide. Is this all right here, whatever I've explained? Can we go ahead, Omkar?
Yes, sir.
Okay. देखो, why I spoke that grass is green on the other side is because see, ये जो electrons है यहाँ पे जो भी electrons दिख रहे हैं ये सब bonds में है और संतुष्ट है. There is no reason why they should go into that particular hole. यहाँ से यहाँ जाने की कोई जरूरत नहीं है. मगर ये जो कहावत है grass is ever green on the other side happens here. And these electrons, what they do is that these electrons which are quite happy in their own bonds, they break the bonds and come up and fill this hole. So actually when we say that holes are charge carriers, it's not that hole is moving, but electrons are moving. And when an electron moves, it appears as if the hole is moving from here to here. All right, so that's how what is the meaning of the phrase? Hare, the meaning of the phrase is grass is ever green on the other side mean like a small child thinks that when you become very big, then I will enjoy life because I'll have money in my own pocket, I can do whatever I want. Okay, but when a person becomes big, he starts thinking that arey itna tension hai life mein, It is better to become small. I really enjoyed my childhood days. I mean, I'm sure many of you all may be thinking the same thing. When I was in school days, it was much more fun. 11th 12th में आके मैं फंस गया हूँ. And then you will think that, okay, let me go into the college, maybe there I'll be happy. And when you go to college, you'll say, "Arey, so boring, yaar. Those days were better." So that's the meaning of this phrase, that grass is ever green on the other side. All right, Sharvari. ओके, दूसरे साइड का जो ग्रास है वो हमेशा हरा है, यानी हम लोग का यहाँ पे जो ग्रास है एकदम सूखा है और वो ग्रास एकदम मस्त है, देखो, like that. So everyone thinks that other person is more happy, you know, like that. So something like that. It's a little bit philosophical, but that's used in English. Yeah. So coming up here, this is a nice diagram from CBSE textbook here, which shows that यहाँ पे 1 minute. I think before that diagram, one more important statement I've written here, and then I'm going to talk about the moving of the electron. सबसे इंपॉर्टेंट पार्ट ये है कि इंट्रिंसिक सेमीकंडक्टर्स में याद रखो कि एक इलेक्ट्रॉन जब छूटता है तो एक होल को पीछे छोड़ देता है, तो नंबर ऑफ फ्री इलेक्ट्रॉन्स इज इक्वल टू द नंबर ऑफ होल्स. ऑल राइट, एंड दिस इज कॉल्ड एज द इंट्रिंसिक कैरियर कॉन्सेंट्रेशन. इसको हम बोलते हैं एनआई. एनआई का मतलब है इंट्रिंसिक कैरियर कॉन्सेंट्रेशन, और ये इंट्रिंसिक सेमीकंडक्टर्स में होता है. और एक्सट्रिंसिक सेमीकंडक्टर में कुछ अलग वैल्यू है. वहां पे एनई एनएच से ज्यादा हो सकता है, नहीं तो एनएच एनई से ज्यादा हो सकता है. मगर इंट्रिंसिक सेमीकंडक्टर्स में जब आप कोई भी इंप्योरिटीज नहीं डालते हैं, तब एक एक जो